Example 22.1 is going to walk us through how to use integration to find volumes. So we've already seen how we can take a line and integrate a line, and maybe it has variable height, but we can integrate that line between two curves, and that recovers an area. Similarly, if we take an area and we integrate it, that builds a volume. So this picture does a pretty good job. We are going to integrate slices of volume. So example 22.1 asks us to find a circular cylinder of radius r is equal to 3, and we're going to cut that at a 45-degree angle and a 0-degree angle as measured from the center. So if I can just rough sketch this, I've got a circular cylinder, and I'm going to cut it at a 0-degree angle, so it has a flat bottom, and from the center, I'm going to cut it at a 45-degree angle. So I'm going to try to draw a decent idea of what's going on here. Here we have our y-axis and our x-axis. And we have a right circular cylinder sitting on top of that. So here's -3, here's 3. And this circle is generated by x squared plus y squared is equal to r squared, or 9. Right, this y value is 3, this y value is -3. And what we did is we took a cylinder that's laying on top of this and cut it at a 45-degree angle. So this is kind of like the back wall of it. Let me see if I can draw maybe a better job of that. So here's that back wall. Okay, so let's try to compute this area. I'm going to think of this area as slices in the y and z. So in the y, that's the length of this, and the z is the height. So the question is, how can we get the height, and how can we get the length? And these will be dependent upon where we are on the x-axis. Am I drawing a really long but infinitely short rectangle, or am I somewhere in the middle where I have a big rectangle? Right, this is going to be dependent upon where I am on my x-axis. So the length here, if I zoom out again, this is given to me by that equation minus this equation. So let's draw that xy plane. There's my x-axis, there's my y-axis, circle of radius 3. The length of these rectangles, this direction, is this length. So we're going to integrate from the top curve, which is y is equal to plus square root 9 minus x squared, just by rearranging this equation, to the bottom curve, y is equal to minus 9 minus x squared inside of a square root. So the top curve minus the bottom curve, maybe this is y1, this is y2, is square root 9 minus x squared minus a minus square root 9 minus x squared. So the length of these lines here, the length of these rectangles, is given to me by square root 9 minus x squared times 2. Now, how can we get the heights of these rectangles? So again, I'm going to try to draw a picture, because as soon as I start adding detail to it, it becomes too complicated. Okay, bad job there, but we figured out how to get the length and the height. If we go out to a distance of x, because this is cut at a 45-degree angle, then the height is also x. Right? At a 45-degree angle, if you go out x, then you also go up x. So the height of these rectangles are also given to us by x. And how do I find the area of a rectangle? It's length times height. This is the area of the cross-section, and we're going to integrate that cross-section from this point, which is x is equal to 0, to this x value, which is x is equal to 3. And that's us integrating from here all the way to 3. And that will build us the entire volume. So let's run through this. We have integral from 0 to 3 of 2x square root 9 minus x squared, and this screams u substitution. U can be 9 minus x squared, du is then minus 2x dx. So we can rewrite this as an integral in u as minus the integral from some lower bound to some upper bound of square root u. I'm not going to compute those bounds because I'm just going to integrate and then put it right back into x. So this is minus the integral. Oops, actually, I'm ready to integrate now. This is minus the integral of u to the 1/2 is u to the 3/2 divided by 3/2, which will integrate between the unknown bounds. And the reason I don't want to find those is because I don't have to. I'm going to take that u variable right back to x. And now that we're back in the land of x, the bounds are between 0 and 3. So if I plug in 3 into this antiderivative, 3 squared is a 9. So 9 minus 9 is just 0. 0 to the 3/2 is just 0. 0 times anything is 0. So the upper bound is 0. I'll subtract the antiderivative at the lower bound. If I plug in 0 for this x, then I have a 9 being square rooted, so that's a 3, but then it's being cubed, so that's a 27. So we have a minus 2 times a 27 over a 3. That gives us a positive 2 times a 9, or an 18.